In this video, we're going to look at how to solve radical equations, specifically those with square roots in them. And what we'll find is that the process for solving these equations is going to feel very much like an echo of what we did when we solved absolute value equations. We will isolate, remove, and solve. When we were working with absolute values, we got the absolute value by itself, and then we removed it so that we could solve what was left. In these equations, I will get the square root by itself. I will find a way to remove the square root so that I can solve what's left. So in this particular example, the isolation step has already been done for me. This square root is already by itself on the left. What I'm going to do is, as I attempt to get x by itself, again, I have all these symbols attached to it on that left side. My job is to remove those symbols from the outside working in. Since the square root is the outermost symbol, I'm going to remove that square root using its opposite. The opposite of a square root is a square. So I'm going to square the left side. And on the right, I have a 5. Remember, I have to maintain balance. So if I square the left, I'm going to need to square the right. When the square undoes the square root, I will be left with 2x plus 1 on the left. On the right, 5 times 5, or 5 squared, gives me 25. Now be careful here. When we were doing the square root property and a square disappeared, then a plus or minus came in. This is not a square disappearing. This is the square root going away. There is no plus or minus when we're working with these radical equations. To square something keeps it positive. To square something keeps it positive. There is no plus or minus. So now I have a nice linear equation. I have x with some numbers. Let's remove those numbers to get x by itself. First, I will relocate the 1 through subtraction. Then I have 2x equals 25 minus 1 is 24. And now to isolate the x, I want to divide both sides by 2. This leaves me with x equals, and then 24 over 2 will give me 12. And I get one solution here. Now with the radical equations, they're a little tricky. Sometimes I will have one solution, sometimes I'll have 2, and sometimes I'll have none. It's very similar to when we did the absolute value equations, and there were those 3 different scenarios. Now one thing I want to tell you about when we are solving, I'm just going to put a little asterisk here, we need to be careful when we're solving. When we have a solution, we have to check it. And I want to explain why we have to check it. Let me go off to the side here. And I'm going to give you a couple of statements. I'm going to say 3 is the same as 3. I'm also going to make a statement that says 3 is the same as negative 3. Now when you look at those statements, you can say, okay, well 3, yes, that is the same as 3, so that's a true statement. And I'm sure you can agree that 3 is not the same thing as negative 3. That would be a false statement. But here's what I want you to see. If I take a true statement, like 3 equals 3, and in that statement, I square both sides. 3 squared on the left becomes 9, and 3 squared on the right still is 9. And so in the end, after I've squared both sides, this has remained a true equation, a true statement. However, let's look at this other statement. This statement, which was false, 3 is technically not the same as negative 3. And so if I were to take that statement and square both sides here, on the left, 3 squared gives me 9, and on the right, negative 3 squared gives me 9. And this has become a true statement. So there is a danger that accompanies squaring both sides. There's nothing wrong with it. In fact, in this case, it maintained a true statement all the way through. Squaring both sides kept the statement just as balanced and accurate as it was. But if I started with a false statement, it was possible that through squaring both sides, I made that false statement look true. And so I have to be really careful when I square both sides that I didn't get something that looked like a true statement when it really should not have been. So all that really means to say is that when you solve, you have to check your answer, because things may look good at the end, but maybe it was false to begin with. So whether or not I did all the math correct, I still have to check my work. Most of the time, I only check my work to get those butterfly feelings in the pit of my stomach that say, yay, I did it right. But in this case, it's not about feeling good about it. It's about something could have gone wrong here when I squared both sides. I have to check this no matter how perfectly I did this work. So let's go off to the side and check our work. What I will do is I will plug in 12 where I see x in that original statement. So let's take that original statement, square root of 2x plus 1 equals 5. I will replace the x with a 12 and just see if this still turns out to be true. So this is just me checking my work. This is just me checking my work. So where there was an x, let's put a 12, because that's what we think x ought to be. Let's put a 12 there. Everything else I'm going to copy. And really, since I'm checking this, I should be putting a question mark over these equal signs, because I don't know if they're equal. I want to check to see if they are equal. I want to check to see if this is a true statement. So now let's go over here and crank this out a bit. I want to order of operations, multiply before I add. So 2 times 12 gives me 24. I want to know, is this the same as 5? This is actually the square root of 24 plus 1 is actually 25. I want to know, is that the same as 5? And yes, the square root of 25 is 5. So when I'm asking, is 5 the same as 5? The answer is yes, so this checks. And I'm going to go ahead and leave that answer. Now, if in this checking process I got a false statement, I'd have to throw that answer away because it wouldn't work. And we'll see that example come up shortly. So again, as I'm solving these radical equations, I want to isolate the root, remove it, and then solve. In this example, I see the square root here, but because that root bar does not extend any further than the 3, I know that this -1 needs to move to isolate the root. Let's relocate that 1 using addition. So I now have the square root of 4x minus 3 by itself on the left. On the right, 2 plus 1 will give me 3. So now that the square root is by itself on the left, I can work to remove that square root. So it's isolation and now removal. To remove a square root, all I need to do is square both sides. And while we'll have to be cautious about our answer because of this squaring action, there's really nothing wrong with it as long as we're doing it to both sides. So now squaring the square root will make that root disappear. On the left, we'll have just 4x minus 3. On the right, 3 squared will give me 9. Now I have a nice linear equation to solve. To get x by itself, let's first relocate that 3 using addition. We now have 4x equals 9 plus 3, which is 12. And so my last step to isolate the x is to remove the 4 using division. 12 divided by 4 gives me 3, so my solution is x equals 3. But really, before boxing that answer and calling it a day, we need to check it. Because again, even if I did all my math correctly here, it's still possible that this action of squaring both sides has taken a statement that was originally false and made it look true. So I do have to check my work here. So let's go off to the side and do that check. What I'll do is I'll begin with the original statement, 4x minus 3 under a square root minus 1 equals 2. And I want to know, does it equal 2? So I'm going to put a little question mark there. And what I'll do is I will replace the x with the 3 that I think it equals. So 4 times 3 minus 3 under the root minus 1, does that equal 2? Multiply before we subtract, so under this root I'll have 12 minus 3. And again, I want to know if this equation's true. 12 minus 3 is 9. Square root of 9 is 3. And I want to know, does 3 minus 1 actually equal 2? And it does. So this is just fine. This checks out just fine. And so I can go ahead and box my final answer of x equals 3. We've already verified that it works. And again, we have one answer in this particular case. Let's just take a look at several other examples to get some more practice. Again, our first step is to isolate the square root. So in this case, when I have a 2 attached by multiplication and a 6 attached by addition, those two pieces need to move. The 6 is farther away from the root because it is a separate term separated by addition. The 2 is part of the same term, so it's closer. Let's remove from the outside in. So let's first relocate that 6. We will subtract to relocate it. We wind up with 2 times the square root of 3x minus 4 on the left, and on the right we have negative 6. So now we want to, again, keep working to isolate that root. I can divide both sides by the 2. That will leave me with the square root of 3x minus 4, now isolated. On the right, negative 6 divided by negative 2 is negative 3. So now the root is totally by itself. We now want to remove it. We'll remove a square root using a square, which is fine as long as you do it to the other side. And the square will undo that square root, leaving us with 3x minus 4. On the right side, negative 3 squared will give me 9. And now I have a linear equation which I can solve pretty easily. I'll start by relocating the 4 using addition. That gives me 3x equals 9 plus 4, which is 13. Now to get x by itself, I need to divide by 3. So now x equals 13 over 3. Now there's nothing wrong with having a fraction answer, but I do need to check this answer. So let's plug it in and see if this checks out okay. So I'm going to start with the original. And this is a longer one, so I have a feeling I'm going to run out of room, so I'm going to try and save some space here. I will copy the original, but where there's an x in the original, I'm going to put 13/3 here. Everything else after the x will just be copied. So we'll still have the minus 4 as part of the root, and then plus 6. And we want to know, does this actually equal 0? So I'm going to work with my order of operations. I'm going to work underneath the root to multiply and then subtract. So under the root, when I multiply 3 times 13/3, the 3 is really a 3 over 1. And it's like these 3's essentially cancel. To multiply by 3 and divide by 3, those undo each other. And so I'm really just left with the 13. So I have 13 and then minus 4. And I want to know, does all this actually equal 0? So now working inside here, 13 minus 4 is going to give me 9. Square root of 9 is just 3. 2 times 3 is 6. And I want to know, does 6 plus 6 actually give me 0? It doesn't. It gives me 12, and 12 is not the same thing as 0, so this is not true. So it's a good thing I checked it, because even though all the math I did over here was perfectly fine, this answer is no good, and that's because of this squaring step here. I took a negative number. When I squared it, it turned positive, and that's the part of turning potentially a false statement into a true statement. Here's the thing. If you ignore the square parts that we added on here, I had a square root that was equal to a negative. But we've seen before when we worked with radicals that the principal square root by definition has to be positive or 0. Square roots can't be negative, just like absolute values can't be negative. And so right here I could have seen a contradiction and known that this was not going to go anywhere good. This solution here is no good. So I'm going to cross it out, but if that was my only candidate for a solution and it didn't work, it didn't check out, then my solution here doesn't exist. I have no solution. So again, it's very important to check your work because even if you do all the math correctly, it's still possible that that answer doesn't check out. So in this case, when that one candidate doesn't work, I simply say no solution. Let's continue to take a look at more examples. Again, our first step is to isolate the radical. In this case, isolate the square root. But you can just imagine if I isolate the square root by dividing by 5, I'm going to create fractions. There's actually a way around that. When I say isolate for the square root, I actually can isolate the square root with its coefficient, and that's just fine. So as long as it's a square root term where there is a square root maybe with a coefficient attached to it, as long as there's nothing else added or subtracted, that's considered isolated enough. So I'm going to go ahead and avoid fractions and just leave that 5 attached. Next, what I'll do is I'll remove the square root, but to remove a square root, I need to square. I do need to be careful though that when I square to remove the square root, I am squaring both sides in their entirety. Now when I say square both sides, I don't mean square each term, I mean square each side. So I am squaring the left side x plus 4 all together, not the pieces, and I'm squaring 5 times the square root of x, again the entire thing. Now to square x plus 4 is to multiply it by itself. And there is a shortcut, and we'll start using the shortcut in just a minute here, but if you're used to using the area diagrams to multiply, go ahead and set that up to multiply here before we try the shortcut. To square x plus 4, again, is to say it's x plus 4 times x plus 4. And if I multiply together, x times x is x squared, x times 4 is 4x, 4 times x is 4x, and 4 times 4 is 16. Now you may remember this shortcut that we talked about earlier in the class, that when you square a binomial, there's a shortcut. You can square the first to get the first, you can square the last to get the last, and you can multiply and double it to get the middle. So you can use that shortcut, or you can go off to the side and do the area diagram or your FOIL. But again, you square the first to get the first, you square the last to get the last, and you multiply these and double it to get the middle. So x times 4 is 4x. If I double that, I get 8x. It's the same thing I would have gotten had I done the area diagram and combined my like terms. But if you'd like to use the shortcut to square the binomial, you may. Now on the right side, be very careful. This is not 5 plus the square root of x, nor is it 5 minus the square root of x. There is no foiling happening here. When I take 5 square root of x and square it, what I'm doing there is I am taking 5 square root of x times 5 square root of x. There is no distribution because there's no addition or subtraction happening. This is really like saying 5 times square root of x times 5 times square root of x. I'm just multiplying all these things. I'm not adding or subtracting any of it. And so I can reorder this. I can say this is 5 times 5 times square root of x times square root of x. 5 times 5 would give me 25. Square root of x times square root of x is square root of x squared, which is just x. So if you look at it, since there are no pluses or minuses, you can look at it this way. Take the 5 and square it. Take the square root of x and square it. The square root goes away. It wasn't that easy over here because of the plus sign. I couldn't just square the pieces. I had to square the entire binomial. So be very careful. If there's a plus or a minus, there's more to it. But now at this point, I have a quadratic equation. Notice the highest exponent is the square. And to solve a quadratic, we have lots of different techniques. The first one that I would attempt is the square root property, but I see that if I try to isolate the something squared, it won't just equal a number because there's these x guys in the way. So square root property is out. The next fastest technique would be factoring. And what you'll find in this section as you go to do your homework is that pretty much all of these you're going to solve at this point by factoring. To factor, we need to set this equation to 0. So I'm going to take this 25x and relocate it to the other side. Now I have x squared, and then 8x minus 25x would be negative 17x. Then I have the plus 16, and this is now set equal to 0. So now that it's set to 0, I can begin factoring. With factoring, I look for descending order, which I now have. I try to find a GCF to pull, but in this case, all three terms share only a 1 in common, so there's nothing to pull. And now, based on the fact that there are 3 terms, I'm going to attempt using an X box to factor. And I'm going to take it off to the side so I've got enough room here. For the X box, I'm looking for a certain product and sum to help me find the numbers to throw in. The product can be found by multiplying the first number times the last. So in this case, 1 times 16, which is 16. The sum is always found in the middle, which in this case is negative 17. So the numbers that multiply to positive 16 and add to negative 17 would be negative 16 and negative 1. And because there was nothing in front of x squared, I can just take these numbers and throw them into parentheses. So I've got x minus 16 and x minus 1 multiplying to give me 0. Keep in mind that every single line of work should have that equal sign. This is an equation all the way through. Now, if something times something is 0, one of those factors has to be 0. And since we're going to have a lot more writing to do in these problems, let's just kind of cut to the chase here. If x minus 16 were 0, just imagine writing that linear equation, x minus 16 equals 0. You'd get x by itself by adding 16 to both sides, and so my solution there would be the positive 16. Likewise, if you just imagine setting x minus 1 equal to 0, you'd isolate x by adding 1 to both sides, and so you'd get a solution of positive 1. So I have 2 solutions, which I kind of expect because when I got rid of the root, I had a quadratic, so I'm seeing 2 solutions here. The question is, do they both check as solutions to the original radical equation? So to check it, we're going to be plugging it in. Let's see if we can just kind of plug it in mentally without having to do all the work here off to the side. Let's check the 16. If I plug in 16 where I see x here, 16 plus 4 is going to give me 20. And if I plug 16 in for this x, the square root of 16 is 4, and 4 times 5 is 20. And so I see that 20 equals 20 is a true statement. That means 16 is a valid solution. Just because that one works doesn't mean the other one works. So let's also check the 1 to make sure it's a valid solution as well. So plugging in the 1 wherever I see x, 1 plus 4 is 5 on the left. Again, plugging in a 1 where I see x, the square root of 1 is 1, and 5 times 1 is 5. And I get that 5 equals 5, which is a true statement. So both of these checked out just fine. And on your test, you certainly don't have to check your work on paper, but I'll know if you checked it or not because there will be examples where the answers don't necessarily both check. Let's take a look at an example where one doesn't work. Remember, our first step when solving these radical equations is to get the root term by itself. In this case, this root is attached to another term, 7. I need to remove that 7. And because the 7 is currently positive, I will remove him using subtraction. So I will subtract 7 from both sides. On the left, that leaves me with the original x, now minus 7. This is equal to the root, square root of 2x plus 1. Now that the radical is completely isolated, I can remove it. I remove a square root by squaring it. Just keep in mind that when I square that entire right side, I have to square the entire left side. And I'm not just squaring the pieces, I'm squaring the entire thing. So if you wanted, you could go off to the side and you can actually multiply this as x times x minus 7 times x minus 7. You could FOIL with arrows, you could use an area diagram, or you can use the shortcut. When you square a binomial, here's the trick. You square the first to get the first, you square the last to get the last, and you multiply x times negative 7 and double it to get the middle. X times negative 7 would be negative 7x. If I double that, I get negative 14x. So that's kind of a shortcut to square the binomials. On the right side, if I take the square root and I square it, it just means the root goes away. And so again, in this case, I have a quadratic equation. Notice the highest exponent is 2. This equation, when solved, will give me 2 answers. I'll just have to check to see if they both work. Remember, to solve a quadratic, we have lots of different techniques, but I'm telling you again, in this section, these will all be, for the most part, most easily solved by factoring. So let's set this equal to 0 so that we can factor. I'm going to take this positive 2x and remove it, relocating it to the other side using subtraction. At the same time, let's go ahead and multitask. Let's take this positive 1 and relocate it to the other side using subtraction as well. So now on the left, I have the original x squared. I have negative 14x minus 2x, which gives me negative 16x. And then I have 49 minus 1, which gives me a positive 48. This is now set to 0, and so now I can factor to solve. Again, with factoring, you want to make sure first that it's in descending order, that there's no GCF to pull, and then for a trinomial, we'll try that X box again. So when we're doing the X box, we have to identify the right product and sum. The product is the first number times the last. In this case, 1 times 48 is 48. The sum is always the number in the middle, which in this case is the negative 16. So we're looking for numbers that multiply to 48 and add to negative 16. And I believe that should be negative 12 and negative 4. And when I have those numbers, because there was nothing in front of the x squared, I can just take those numbers and throw them in for my factorization. So I'll have x minus 12 times x minus 4 now equal to 0. Again, don't forget that if it's an equation in the beginning, it's an equation in every single step. So now if something times something is 0, one of the factors has to be 0. If x minus 12 were 0, x would have to be 12. If x minus 4 equaled 0, x would have to be positive 4. But rather than boxing this in and calling it a day, I do have to check those answers, not necessarily on paper, but I at least need to run through the options and verify that they both work. So, if I were to test the 12, let's say that the 12 were on the left side here. Let's say the left side is 12 for x. Let's check and see what the right side says. Plugging in a 12 for x. 2 times 12 is 24. 24 plus 1 is 25. And the square root of 25 is 5. 7 plus that 5 is 12. And so 12 equals 12 is a true statement. I will keep the 12. Let's now test the 4. If I plug in a 4 where I see x, then my left side now says 4. Let's see if the right side matches. Again, plugging in 4 where I see x, 2 times 4 is 8. 8 plus 1 is 9. The square root of 9 is 3. And 7 plus 3 is 10. But 4 does not equal 10. This is a false statement to say that 4 does equal 10. And so 4 is a solution that is what we call an extraneous solution. It's something that worked through the algebra but doesn't actually represent a true solution when I plug it in. 4 does not equal 10 when I plug it in. And so here my only solution that actually works is x equals 12. So again, if you get a solution that when plugged in doesn't work, we call that an extraneous solution. It's an extra solution that we got through the algebra that didn't actually check out in the end. So in this case, even though we saw a quadratic, we only had one solution in the end for this radical equation. Let's take another look at an example just like this. Again, our first step is to isolate the radical. So I see a radical term here attached to an x term. Let's take that x term and relocate it. Since it's positive, I'll relocate using subtraction. And so I wind up with negative square root of 1 minus x equals negative x minus 5. And I'm noticing something interesting here. When I relocated that x to the other side, to get the root term by itself, I'm noticing everybody is negative. What I'd like to do, just for convenience, because I don't like all those negative signs, let's divide by this negative that's in front of the root. So it's like the coefficient on that root is a -1. If there's a -1 multiplied to the root, let's remove it using division. Again, remember, you have to do the same thing to both sides every term. So on the left side, this is only one term, -1 of these roots. When I divide -1 by -1, that negative goes away. But notice the stuff under the root has not changed signs. I'm dividing by the coefficient stuff. Now on the right side, negative x divided by -1 is positive x, and -5 divided by -1 is positive 5. So each separate term gets changed, or its sign gets changed. So this one term changes sign. These two terms change sign. And now again, that root is isolated, but it looks a little bit cleaner without all those negatives. So now that the root is by itself, we can remove it using the square. The opposite of a square root is a square function. So to square the square root makes that root disappear. I have 1 minus x. And then on the right side, when I square this binomial, notice the plus sign, this binomial, I don't just square the pieces, I'm squaring the whole thing. So this is x plus 5 times x plus 5. And you can either set up an area diagram or FOIL, or you can use the shortcut. To square a binomial, square the first to get the first, square the last to get the last, and then multiply and double to get the middle. X times 5 is 5x. If I double that, I get 10x. And so now again, I have a quadratic equation. And like I said before, even though you have several techniques for solving quadratics, each of these should be most easily solved using factoring. Let's set this equation equal to 0. Since my x squared is on the right side right now, I'm going to push everything to the right side. It doesn't ever matter which side you choose, but because when I factor, I like my first guy to be positive, I'm going to move to the right. So this positive 1 will relocate with subtraction. And while I'm at it, let's multitask here. Let's take this negative x, let's relocate it with addition. And so on the left side, everything cancels away and we have 0. On the right side, I have my x squared. I have 10x plus x. You can think of that as 10x plus 1x, which gives me 11x. And then I have 25 minus 1, which is 24. So now I have a trinomial. 0 equals this stuff. Now, if it bothers you to have the 0 on the left, you can just put the 0 on the right because equations can be read in any direction. 0 is the same as this trinomial. Could be said, this trinomial is the same as 0. So it doesn't matter what side. And if you like the 0 on the right, you certainly can move it just like that. But now that it's set to 0, I want to factor to solve. So let's find our magic numbers using our x box here. The product is going to be your first times your last. So here that's 1 times 24, or 24. Your sum is always found in the middle, which in this case is 11. So the numbers that multiply to 24 and add to 11 will be 8 and 3. And because there wasn't anything in front of that x squared, I can just throw those numbers into parentheses. So x plus 8 times x plus 3 But do remember, all along this process here, it's an equation, and then this last step we said this equation is equal to 0. And if something times something is 0, one of those factors must be 0. If x plus 8 were 0, then x must equal negative 8. If x plus 3 were 0, then x must equal negative 3. Again, even after all the work we've done, we don't want to just blindly accept these because one or both of them could be extraneous solutions. So we have to take these and go back to the original to check. Let's try the negative 8. So everywhere I see an x, I'm going to put a negative 8 instead. So let's say this x is a negative 8 here. If I had 1 minus negative 8, that really means 1 plus 8, which is 9. The square root of 9 is 3. Negative 8 minus 3 is negative 11. That's not equal to negative 5. And so negative 8 doesn't work. It's called an extraneous solution. But let's try the negative 3. Let's now instead suppose that x is negative 3, and let's see if this works. 1 minus negative 3 means 1 plus 3, which is 4. The square root of 4 is 2. Negative 3 minus 2 is negative 5, which does in fact equal negative 5. So negative 3 works. The negative 8 did not. So I'll write only negative 3 as my solution. So as you're going through these problems, again, keep in mind the 3 main steps. You want to isolate your root term. You want to then remove the square root using a square. And then you want to solve. But again, in that last step, when you solve, do be careful to plug things in to check, to make sure that any of these are not extraneous solutions. If they are, we cut them out and only accept those answers which did check accurately. In the next section, in the next video, we're going to be looking at a different kind of equation called a rational equation, and we'll learn how to deal with fractions in equations.